Okay, in yesterday's class, I showed you how to extend the derivation for flow and settling of spherical particles to any arbitrary shape. So basically, you defined parameters that were kind of shape independent, right? And you rewrote the equations of motion for settling in any force field. So we were then worrying about what to do about the individual components of in this force balance, right? And we said, well, we can define the buoyancy force also in shape independent terms. And then we also looked at the drag force. So let us just start from there. And then let's just start from the drag force so that those who weren't there yesterday will just get a nice revision of that. So let me share it. Let us see if that shows up. One minute. The older slides. Right. Right. So this is where we were. Shape, solid sphere. We saw how to remove that. The acceleration term equal to 0. We saw how to remove that approximation because we now have the complete with the acceleration, or even in the centrifugal field, we can write those equations today, right? And the field was not limited to, therefore number 4 was also taken care of. We need to, however, worry about number 2, but we will do that one step at a time. So what we did is, if you look at this slide, we defined the CD as the dimensionless drag coefficient. And we said that the appropriate area is the projected area of that particle, irregularly shaped particle, perpendicular to the direction of the motion. If it was settling, it was moving vertically. And then I asked you to recast all of these into the terms of the body force, the buoyancy force, the drag force times the mass times the generalized acceleration. And the equation of motion should look like this, so you should be able to derive this. Can you see this? Is it large enough? So please derive this. And moreover, this is written for a generalized acceleration A subscript E. So please adapt it to the first to the case of gravity settling that we considered, the special case. I mean, quite an important case because there are so many sedimentation type applications. Then you can also replace that RE with the acceleration in a centrifugal field and derive the du by dt for a centrifugation application. Please write those equations for those two cases. One for a vertical downward movement of the particle, as would happen under gravity. And secondly, for a radial movement, as you would expect if the centrifugal force were very large. Okay, and I've given you the general equation. So just adapt it and check that that is correct and do it for the two special cases. Right, this equation follows from the deliberations of yesterday. So just see if is my query okay? Is it clear to all the very few students who are attending? But is it okay? Is it clear? What I asked you to just derive? I mean, and check with the what is there on screen. Is it clear? Because we have to go beyond this today. So first let us do this, and then that's why this part must be clear to everybody. Is it all right? Can you hear me? Okay, right?
Yes, sir.
Okay, fine. So check this expression and then do two sub expressions, one for motion in a centrifugal field and B, A, then B motion from gravitational force. Okay, so you will have two expressions of the general equation on your screen. Right, so in the first sub expression of what is on the screen, you will have G instead of A subscript E on the right hand side of this equation. And for the motion in a centrifugal field, you will have R omega squared instead of A subscript E. And in that equation, U is not the velocity downwards, but it is the relative velocity of the particle to the fluid directed outwardly along a radial direction. Okay, that's what the R omega squared in the equation stands for on the right hand side. So now we can always solve this first order differential equation if we know all the material properties of the solid as well as the fluid transport properties. And of course, we have still retained the unknowns or whatever variables we don't know. We have sort of retained them in the term C subscript D. Right? I mean, see, mass we can measure. Rho we know. Rho subscript P we also know from the properties of the particle. U we have to find out. A subscript P we can definitely determine for any arbitrary shape. The only problem, of course, is still CD, which is not yet determined, as Ishika also pointed out. The thing is that CD is a very strong function of hydrodynamics, and we have yet to discuss how that function really translates. So you can say that whatever we do not know about the fluid flow, whatever is unknown about the hydrodynamics, we have put all of those into this fudge factor or into this CD uh, variable. But the good thing is that this CD is evaluatable. So I won't call it a fudge factor. In essence, it is an experimentally determined variable. All right. Now, this CD, of course, depends on the drag force. The one thing is that the drag force itself, it depends on velocity. I mean, you know that expression for the sphere, it was linearly dependent on the velocity, directly proportional to it. Now, that is a very idealized expression for a very low Reynolds number and only for a solid sphere. But one constant thing that is found from all experiments is as the relative velocity between fluid and solid increases, the drag force always increases. It's an increasing function of this velocity. So now if the drag force is an increasing function of the velocity, and then we have the force balance between buoyancy drag opposite to body force on one hand, and the body force on the other hand, then what we would expect is that at some time instant, there would indeed be a balance of the forces. In other words, the drag keeps on increasing with the velocity, and so you would that's a very strong negative force on on the settling force due to the gravity, let us say, or the centrifuge. And so somewhere you would expect the acceleration to keep decreasing. And certainly for gravity, this is a very good approximation. I'm not saying that for a centrifuge, this is a good approximation, but we can use it later. But when we do it, if we reach centrifugation towards the end, which we hope to do, we will try to alter that assumption also. Because normally the centrifuge is set up with that such that the centripetal acceleration is extremely large. Centrifugal acceleration is extremely large. So the acceleration term actually never drops to zero. But nonetheless, when you have free settling, at least, in other words, there's no interference from other particles, and there is no interference from the wall of the container. Indeed, the acceleration keeps decreasing for the gravity case. And ultimately, it will approach zero. However, you can solve the first order equation, differential equation, and see for what length of time this approximation of constant velocity or a terminal condition velocity is applicable. The good thing is that if this is approached in gravity settling after some time t, then you can replace that velocity, which was a variable in the equations of motion, by a constant velocity u subscript m for maximal or u subscript t for terminal. Both notations we can use. So what I would now want you to do, at least, which is, as I said, a very good approximation for settling in free settling in under gravitational conditions. I want you to knock off that mass times acceleration or acceleration term as given in the slide and obtain the general equation for the maximal velocity. So this, I call it general equation because nowhere you have said it's a sphere or it's a cylinder. There's no definite shape. You have not said anything about the hydrodynamics because that's contained somehow in the CD. How we are going to recast it to the actual flow situation is a topic for next week. But that also approximation, there's no such approximation that we have made. And in principle, we can solve the first order equation, so we have not even worried about the constants thing. But now we are going to put du dt equal to 0. And now I would like you to solve for a arbitrary shape, the maximal velocity that you can get first under gravity settling, and then assuming the same approximation applies for centrifuges, I want you to derive the expression of constant terminal velocity, not such a great approximation, but nonetheless, assuming that you can make those assumptions, constant maximal u, I want you to derive that maximum velocity for the centrifuge. And tell me what expression you get. Right? So my question is, now knock off that acceleration du dt term and obtain me, because slowly that acceleration term is going to decrease because of the way the drag force keeps increasing as the u keeps increasing. And if it becomes very small, I can neglect it. And then I have a regime where the velocity u approaches a maximal and a constant value. I want you to find that maximal or terminal condition value and give it a subscript T or M or terminal or maximal. To transpose the terms on the right hand side and solve for the constant u equal to um or ut and obtain a final expression. Anima, is my question clear to you?
So actually, I had internet problems and I joined just now.
All right. Can you see the screen?
Yes, sir, now I can.
Right. So this is the general equation. Now I'm not going to, I already repeated what we did yesterday in concise form for in 10 minutes. But I can't go through it again. It will look very funny otherwise in the recording. But assuming you start from this general equation, Animaji, what is on the screen,
Yes,
and
sir.
then knock off the acceleration term du dt, I said that you will get a general expression which is shape independent. Nowhere we have assumed anything about shape. Nowhere we have assumed anything about hydrodynamics. Okay, and so hydrodynamic regime independent, shape independent expression you are going to get for a maximal velocity or a terminal condition velocity u subscript t or u subscript m. So I said, please solve for that and tell me what that expression looks like.
Yes, sir. I will do.
I hope you're as thin as ever.
Yes, sir. That doesn't seem to be changing anytime soon.
Good, wonderful. I remember you all from, I have a good memory. So, and actually, I remember your batch, your class at least. So if I were to ask you that what I mean, what are all the variables in terms of which you can get this maximal velocity? What are those variables? Tell me once you solve. And then we can discuss that solution further. Because there are so many other sub applications and sub constraints that we can make onto that solution. But first you must derive that. And imagine we are still doing free settling, okay? And we only have single particles. So imagine if we were to, as I said, there's no exact solution the moment the settling becomes hindered. But one thing we know is that the presence of other particles, as we would expect in a bed of solids or in a filtration application, the terminal condition velocity which you're going to derive for the free settling case, it is always going to decrease. The factor depends on how much depends on the situation and on the bed and on the porosity and so on. Anyway, so first let us get this general result. You should find this relationship. Anima, can you see this new slide?
Sir, I'm still on the old one.
Okay, but you should be able to see the new one. So this is, please check that you get this final expression for maximal terminal U. Once you have derived it, I would like to discuss this expression further. Or once you verify what's on screen. So the expression for gravity settling that you should get for the maximal velocity U subscript T is equal to hole within undergoes twice G difference in the densities rho P minus rho times the mass of the particle upon the product of the projected area, particle density, fluid density, and the drag coefficient, everything to the raised to the power half. Okay, this is the expression that you ought to get. Now, in this expression, have you made any assumption that it is a cylinder or it's a sphere? Not at all. This is a very general expression. There is no shape dependence in this. Of course, that's a different matter, that CD itself will be different for different geometries. That we accept. But as far as this expression is concerned, if you had a sphere, if you had to were to put the correct CD for the sphere, because you know the drag force, you can always derive the CD, because you just we just had a general expression for half rho u squared into of CD into AP's drag force. So you can always obtain the CD for the sphere, right? There's not a problem. So, but as far as this expression is concerned, you haven't assumed any geometry. Now, projected area is also a general concept. I can project any irregular shape onto a plane perpendicular to the motion. Why not? M I can measure, rho I know, rho P I know, AP I can obtain by the projection. In delta rho I know, G is G, but you can also obtain another expression like this, which I haven't put down here, but replace the G by the R omega squared. So the R stays within the square root and omega squared, so omega comes out. So the expression should be U subscript T is omega, and then within under root twice R rho P minus rho M upon AP rho P rho into CD, right? This is the other expression, sister expression for the centrifugal force, centrifuge. So I mean, whatever we discussed for gravity is also applicable for a centrifuge. The only thing is later on we have to, centrifuges come in very complex geometry. For instance, they have vanes, they have, to increase the area that you can give for the settling. And then there is a very conical type of arrangement for that. It's or a disc type centrifuge as it's called. So, it's not, if it were just a simple cylinder, much easier for us to do all the geometry. You can use this R omega squared very easily, but okay, they come in all sorts of shapes and sizes. So the centrifuge, so it requires a little bit different analysis, but this expression is still valid within the assumption for the centrifuge of constant or du dt equal to 0. Okay, so there is no assumption here about shape or about hydrodynamics. General expression. Only thing you have said is du by dt is small or 0. And even that we know how to eliminate that assumption, because you have the complete equation of motion. So only thing is you have to solve for. So essentially you can integrate it, and if you know the initial condition. Is everybody with me? Good. Now we need to worry about CD, a point that Ishika made. But before we do that, I would like you to check one more thing. See, we started out with the sphere, and now we have a shape independent expression. Why can't we adapt this to a motion of a spherical particle under any hydrodynamic condition? Right? It could be Reynolds number 1, it could be Reynolds number 1000, it could be 2100, it could be turbulent flow 10 to the power 4, 10 to the power 5, anything. So why don't you replace the variables in this general equation for U subscript T and adapt it for a sphere? So the small m that you have, the mass, please write that in terms of the diameter dp of the sphere. Find out the projected area of that sphere, and then obtain me a general equation which is valid for any flow regime, but now it's only for a sphere. Don't forget that our Stokes law expression is even more specialized special case. Okay, here I am not telling anything that Reynolds number should be less than 1, nothing. But this general expression, you can now adapt it to a spherical geometry. So just And later we would like to know if we can adapt it, we can obtain the sphere's Reynolds number less than 1 expression as we further put constraints. That's what I want to do today. So what you have to do is what is in the next slide. It will show up soon for you. The mass can be now represented in terms of the particle density and the sphere's diameter. And the projected area of the sphere is just 1 by 4 pi dp squared, right? Pi r squared, essentially, the cross-sectional area. That is the correct projected area of that sphere. So now we can substitute this into the general expression for the terminal condition velocity. And we will have a general equation for the gravity settling of spheres independent of the flow regime. So please tell me what you get. You should get a very well-known equation, a general equation now for spheres though, but for any flow regime. Could be Reynolds number 1, Reynolds number laminar flow, creeping flow, turbulent flow. And this is that expression. The terminal condition maximal velocity is within square root 4g into the difference in the densities between the particle and the fluid surrounding it, multiplied by the particle diameter, whole divided by, still within under root of course, thrice the dimensionless drag coefficient times the fluid density. 4g rho p minus rho dp upon 3 cd rho. Very important expression. So please see that you can derive this. Now what I would like you to do finally is, you see, for the Stokes type of flow, the CD is given by a very well-known expression which you would have done in Bird-Stewart-Lightfoot, except that he expressed it in terms of F. But nonetheless, in that creeping flow, the CD is always inversely proportional to the Reynolds number. So can you remember that expression? Can anybody tell me what that expression was for very streamlined flow, or RE less than 1 in our case? So the friction factor was 16 by RE or 64 by RE, but when we have the drag coefficient CD, it was 24 by the Reynolds number. Okay, that is what it was for creeping flow of a sphere. So now you can take this general expression which is valid for sphere in any Reynolds number for any dynamics, flow dynamics, and limit it to the case of the creeping streamlined flow. and then see whether you can derive the Stokes velocity that you first started with when you started the course with, which was the GdP squared rho p minus rho by 18 mu dependence. You should be able to do that. Okay, you get what we are trying to do. Rather than start with a very specialized shape, a very specialized flow regime, we are starting with a very general expression, which even valid for an accelerating frame. Then we gradually, one by one, we limit it. First to du dt 0. Then we limit it to the geometry. In this case, for a sphere, we get a general expression. Now we are trying to limit it to the very special case of the creeping flow of Re less than 1, which is given, which gives the inverse dependence of the CD on the Reynolds number. Okay, because that is the characteristic property of the creeping flow regime. And now when you substitute for that in this general expression for the spherical particle, you should be able to get the derive the terminal expression, terminal velocity expression for the sphere in Stokes's flow. That is the G with the dp squared, square on the diameter dependence. So please see that you can derive GdP squared rho p minus rho by 18 mu from this by limiting further this general expression for the sphere for Reynolds number less than 1 and using the well-known dependence, inverse dependence of the drag coefficient on the Reynolds number, particle Reynolds number, I should say. Okay. So you should be able to put CD equal to 24 by Re, substitute that in this expression within the square root and obtain the Stokes dp squared dependence that we first derived in our very first class. All right. Of course, now we have only done for a very limited situation Reynolds number less than 1. What do we do if the Reynolds number is higher? A very much more interesting question. So next week, I would like to take that up. And as I have repeatedly said, if you were to just not look at the hydrodynamic regime, you will estimate, you will underestimate or overestimate the drag force by orders of magnitude. For instance, if the Reynolds number were 10 to the power minus 5, and you want to go to 10 to the power plus 5, which is the 10 decades of range that I want to take up, over the 10 decades of Reynolds number, the drag force will change by, let us say, 5 orders of magnitude. 5 orders of magnitude. And as you know from the viscous dissipation point of view, when the Reynolds number is low, the drag force is far, far higher. And it shows this logarithmic dependence that you just now saw with the 1 by Re dependence at very low creeping flow regimes. So the resistance keeps falling and you can decrease the drag force by over 4 to 5 orders of decades of magnitude. Therefore, it is now very important for us to look at how we can obtain this drag reduction as we increase the Reynolds number. Okay, but first I would just like you to derive one by one all these limitations. Start from the general expression for the acceleration, write it for both the cases of gravity settling and the radial movement in a centrifuge, then put the du by dt term negligible equal to 0, then solve for the maximal velocity for shape independence as well as regime independence, then obtain general equation for a sphere for any Reynolds number, then further limit it to creeping flow with the inverse dependence of drag, dimensionless drag coefficient CD on the Reynolds number and obtain the Stokes velocity. Okay, and then let us see how we can go to Reynolds number above the creeping flow. All right, and that we want to finish next time, and then we can worry about going to more than one particle, for which, as I said, there's no perfect theory, but what is it that we get can be done, and then there are applications in filtration and all where we take up those type of Darcy's law type of things for several particles that are interacting with each other, and it's a constitutive equation. We don't have perfect theory, but for single particle we do have a perfect theory, right? That's what we will try to complete next week. Okay.
Yes, sir.
Yes.
All right. Very nice. And see you again then next week.